Well, I'd like to welcome everybody to this webinar, this virtual event here at Magdalene. The topic of the event is the Zoologist's Guide to the Galaxy, and it's just got lots of wonderful words, so evocative to make us think about the whole environment of space, but also of the world that we're more familiar with and how those two might intersect with each other. It's a big thrill to have here Dr. Arik Kershenbaum, who is going to introduce the topic by talking a little bit about his most recent research. Professor Tim Clutton-Brock, who's going to join Dr. Kershenbaum in a roundtable discussion a little bit further on, along with Professor Martin Rees, Lord Rees, the Astronomer Royal, who's also going to join in with that discussion. I'm just going to start really by introducing our three main speakers. Dr. Kershenbaum is a Magdalene person. He matriculated here in 1984, reading natural sciences. He's a fellow and also the Director of Studies in Physical and Biological Natural Sciences at Girton College. His research focuses on animal communication and particularly the information content in high social and cooperative species, particularly predators, cooperative predators, such as wolves and dolphins. And if I get the chance, I shall ask him whether we should reintroduce wolves into the UK or not. I don't know if he has a view on that, but perhaps later on. Lord Rees, Martin Rees, of course, very well-known here in Cambridge, formerly the Master of Trinity College, an astrophysicist, cosmologist, and the Astronomer Royal. He's based here as the director of the Institute of Astronomy, professor of astronomy. And his main astronomical research interests have been galaxy formation, cosmic jets, black holes, and gamma ray bursts, which sounds rather to me like this series of names of most wonderful ice creams. This might be because it's such a warm day today that I may be thinking of ice cream, but it's an absolute delight that he is joining us. And he's also interested, and maybe we'll have a chance to talk about this, in the prospects of detecting extraterrestrial life as well. Our own Professor Tim Clutton-Brock matriculated here at Magdalene in 1965, read physical anthropology. He's a Life Fellow here at Magdalene and works on comparative studies of the behavioural ecology of mammals, and particularly very important and influential work on red deer and on meerkats. Indeed, he just told me a few minutes ago that Meerkat Manor is back on course for another series, so that'll be fantastic. He was awarded the Darwin Medal from the Royal Society in 2012 for his work on the diversity of animal societies, and he works on demonstrating the effects of animal societies on the evolution of particularly reproductive strategies and the operation of selection, the dynamics of population. So we're absolutely thrilled to have three such very distinguished speakers. Very pleased that Arik is going to start off by talking about his own work, and then we're going to have a chance for a roundtable discussion. Just from the sort of technological point of view, first of all, I'd like to thank Emma and Sarah, who are lurking in the background. So if I have technological problems, they're going to bail me out. But I'd like to thank them for all their help in putting all this together. And also just to say to all of those people here that we do hope you will join in the question and answer session towards the end of our hour. If you look down at the bottom of the screen, you'll see that among the options down at the bottom, there's Q and A. There are two little speech bubbles. If you just click on that, you'll be able to put your question in to the Q&A question list, and I'll go through as many questions as I possibly can for our speakers. So that's enough of me. Perhaps the one other thing I should just say is to apologise on behalf of the Master to Chris Greenwood, who would have loved to be here. I know he was very much looking forward, but he's just had a hip operation. And although he's making very good progress, I think the general advice from his doctors, and more particularly his wife, was that he really had to take things easy tonight. So you've got me as the president of the college. So I'd like to start off by asking Arik if you would like to begin by giving us a presentation about your most recent research, and then we'll move on to the roundtable.
Sure. Well, thank you very much. Thanks for the introduction and the invitation to be here. It's a fantastic topic to talk about because it's a fantastic time to be thinking about these things. I mean, we are in a phase of incredibly rapid discovery when it comes to questions of astrobiology and life in the universe, in a way that couldn't have been said 10 years ago or 20 years ago. We're very, very confident that there is life elsewhere in the universe. We don't know what it's like. We don't know really anything about it, but we're confident that it's there, and we're confident that there will be very important discoveries in the coming years. That means that we have to come to terms with the fact that we will be soon discovering alien life, or the existence of alien life. And that means it's important for us, both as scientists and as members of the wider community, to be in the right frame of mind. We need to be ready for this discovery. On the one hand, obviously, it's going to affect us in terms of how we think of ourselves, how we think of our place in the universe, how we think about humanity as a whole, especially if we end up discovering intelligent aliens, which I think is unlikely. But in any case, even any kind of life will change how we think about ourselves and our place in the universe. But as scientists, it's also very important to be ready for these discoveries. We don't want to get caught with our pants down. We don't want to find that there's life elsewhere and we haven't even thought about how we're going to investigate it, what it might be like, how it might have evolved, what forms it might take, what diversity it might take. And people are working on this. This is an idea that's beginning to gain some traction. But of course, until you have any data, until you have any information, it's very difficult to know what to prepare for. There was an interesting example of a really good way to deal with this just recently, just last year, when there was a discovery of possible existence of phosphine gas on Venus. And the team that made this discovery, one of the team members here in Cambridge, came up with a hypothesis for a ecological scenario in which there could be life in the clouds of Venus and producing this gas. And it was based around tiny droplets of ultra concentrated sulfuric acid containing a single microscopic unicellular organism. And as the drop would descend in the atmosphere, dry out, the organism would become dormant, become a spore. And then as it was lifted up again on air currents, and the acid would condense around it again, it would become active and divide and reproduce. Completely speculative, but at least it's a way of thinking about how this life could have existed. The thing about the suggestion, of course, is that it's very simple, but it doesn't raise a lot of the questions that we as earthbound zoologists think of, which is things like, well, are these organisms interacting? Do these drops ever coalesce? If they were to coalesce, then perhaps there would be the opportunity for these microscopic organisms to reproduce sexually. What impact would that have? So this idea of changing the way we think about alien life, not just to be discovering it, but also to think about what it would mean when we do discover signs, symptoms, any kind of indication that there might be alien life. Now, of course, without data, it's very problematic. What are we basing all these predictions on? How can we make any kind of reasonable assumptions about what alien life might be like? there are answers to this, and the answers are based around the idea that life is constrained. Life can't be just anything. There are very real constraints on what makes life life. And those constraints are based on rules and laws that we know, we're familiar with, we're confident that they apply everywhere in the universe. Some of them are very simple. Some of them are the laws of physics. The laws of physics, they're going to apply everywhere. The laws of mechanics are going to apply everywhere. If you are a moving organism, you have to move according to those same mechanical laws that dictate how animals on Earth move. If you're moving on a solid surface, it's pretty useful to have legs. Legs reduce your friction between you and the surface and still give you the ability to exert a force and move yourself forward. If you want to fly, there aren't that many ways of flying. There just aren't actually all that many physical techniques by which you can fly. And life on Earth seems to have exploited pretty much every way of walking and of flying. So it makes a lot of sense that we can expect similar behaviors, similar ways of getting around on other planets. The other example, of course, is sensing the environment around you, using light, using sound. These are the laws of physics acting, and they're going to be the same on other planets. But beyond these physical laws, beyond these rather simple and familiar physical laws, there are other constraints that are acting on life. And the biggest constraint is that life must have evolved through natural selection, because complex life can't just pop into existence. It's just too unlikely. So if there is life on other planets, it must have arisen through this gradual accumulation of complexity that is what we call evolution by natural selection. But I think we'll talk about that a little bit later and ask whether that really is the only way that it could happen. But it does still impose constraints on the nature of life. So, for instance, we know that all life needs energy. This is a fundamental feature of life for reasons of physics as well. But if energy is limited, if there's not unlimited energy, then organisms will be competing for that energy. And if a planet is covered with photosynthesizing organisms that are just absorbing energy from their star, which is in most cases the most available, most plentiful source of energy, sooner or later, an organism is going to come along that can take its energy by ingesting other organisms, not by waiting for the sun, but by exploiting others. And this, if it can happen, given enough time, it will happen. So things like predation are very fundamental to the way that complexity accumulates in life. These are things that we can expect. Another perhaps surprising feature of life that is almost inevitable is intelligence. Intelligence is just a way for an organism to make accurate predictions about the world around it, to decide what is going to serve it well and what is going to serve it poorly. It doesn't matter if it's an amoeba that's following a chemical gradient or if it's a human manipulating the stock market. These ways of interpreting the environment, interpreting the world around them, that will give them an evolutionary advantage. These are things that are going to evolve. There are other constraints on life that are perhaps even more surprising. They are concerned with interactions between organisms. They're concerned with mathematical principles like game theory. So game theory dictates a lot of how animals on Earth interact with each other. But there's nothing specific about Earth that involved in these laws. These are simply mathematical tendencies that are likely to exist anywhere. And these dictate things like how much an animal might cooperate with other animals or compete. What's the balance between cooperation and competition? Will societies form? Under what conditions would societies of alien animals form? Yes, the details would depend on the details on these planets, but the principles are principles that we've uncovered on Earth, and so we can apply elsewhere. So in general, I suppose what I'm really saying is that we think about astrobiology, many people are involved at the moment in the search for extraterrestrial life. This is really important. We need to know what it is. We need to know what it's made of and how it works. But we also need to think of the broader relationship between these life forms on alien planets. There will not be an alien planet with a single life form on it. There will always be a diversity of ways of surviving and living, and that means there will be an ecosystem, there will be interactions. We need to think of astroecology as well as astrobiology, and how what we've discovered from looking at the interactions of organisms on Earth gives us the fundamental tools to understand and be prepared to investigate life on other planets. So that's my sort of brief introduction to how we can reasonably and logically talk about what alien life might be like. I'll hand back to Jane.
Thank you. Well, thank you. That was wonderfully covered so much and so concisely. That was a wonderful exposition of your thoughts. I'd like to initiate a kind of more of a roundtable discussion, perhaps with all three of you involved in this, really based on what Arik has just said. But perhaps I could start off by throwing something in as a question to begin with, and then perhaps between yourselves you might develop the conversation in ways that seem probably more interesting than I'm a medievalist, so that I'm going to be able to think of. But perhaps I could just ask my sort of initial question, which is about how the ideas, the science which is developed by our experience of our own world of Earth and the way that ecology works, the way biology works, how confident we are that that sort of rolls out into other environments, into other possible, planetary environments. One can sort of imagine maybe, with Mars or Venus, maybe you can kind of see that that's almost approachable. But what about in the wider universe? Are we happy that those physical rules, those biological rules that you were talking about, Arik, would actually pertain, in a sort of wider scenario? I don't know who'd like to help me out with that to begin with, and then I will leave you to your own discussion. Arik, do you want to?
I'd like to hear what the other panelists have to say. I think Martin, have you got something to say? You're muted.
Martin, you need to unmute your microphone.
Okay, can you hear me now?
Perfect, that's perfect.
Okay. Well, perhaps I can just say something about the wider context, but first let me say how much I admired Arik's book, and I agree with him that this is an exciting time because many of the questions we're raising will get glimmers of answers, at least in the next 10 or 20 years. It's very exciting. But of course, we have the possibility of probing directly the planets of our solar system and the moons of Jupiter and Saturn to see if there's any form of life. But of course, the exciting thing which revived this subject is that we've learnt, mainly just in the last 20 years, that most of the stars in the sky, like the sun, are orbited by retinues of planets, just as the sun has the Earth and the other familiar planets. And this therefore means that there's a huge variety of planets out there around a range of different stars, including probably in our Milky Way galaxy, many millions of planets rather like the Earth, planets the size of the Earth at a distance from a stable star such that water can exist. So there are huge numbers of possible locations. But the bad news is that these locations are hard to observe, and the planets which are inferred to exist around other stars are actually so far inferred mainly indirectly. We don't see the planet, but we see the effect. We see it if it transits in front of the star, it makes the star a bit dimmer. So we can infer there's a planet orbiting if we see periodic dimmings. So that's how we know about these planets, but we can't see them. But there will be telescopes in the next 10 years that will be able to actually analyze enough light from some of these Earth-like planets around nearby stars to actually learn about where they might have a biosphere. The problem, of course, is that if you look with a big telescope at a star, then the planet is very close in the sky to the star and millions of times fainter. So it's very hard to separate out the light from the planet. But if one can do this, then the experts, and actually I'm not an expert in this area of astronomy, they could tell if there was oxygen, even if there was chlorophyll. So if you had a planet covered with trees, we might be able to detect that. And also we could detect other topographical features of the planet, because to take an example, supposing that aliens were out there looking at our solar system, then the Earth would look, in Carl Sagan's phrase, like a pale blue dot. But the shade of blue would be a bit different depending on whether the Pacific Ocean or the landmass of Asia was facing you. So they could infer that we had oceans and continents and the length of the day. And that's the kind of thing we might one day be able to do for these planets. That'd be really exciting. So that will depend on having better telescopes. In particular, there's a telescope being built in Chile by a European consortium that the UK is in, called unimaginatively extremely large telescope, the ELT, and it's got a mirror 39 meters across, which collects a lot of light, and combined with a high resolution spectrograph, that may be able to do some of this analysis for planets orbiting nearby stars. But let me mention another thing, which is that even though in our solar system we don't expect any advanced life, of course, the probes are now looking for evidence of life, or some maybe long dead life on Mars, and there are possible probes that will be sent to Enceladus, which is a moon of Saturn, where there's water under ice, and Europa, a moon of Jupiter, where that's the same. And they might find evidence of life. And that in itself would be very important, because although Arik said that life is widespread, so long as we have only one example, namely the Earth, we can't disprove the possibility that it's a rare fluke which only happened here on Earth. And there were immediately tell us that life exists in a billion places, because if life originated twice independently in one planetary system, it can't be a rare fluke. It must exist everywhere. And so that's why these experiments to send robotic probes to the outer planets are very important, because they would help to answer that overwhelmingly important question. So I'm very excited, as you gather, about what we can learn, which would be the basis for everything that Arik's done. And I remember when I heard Arik speak once before, the question I asked him was, if we got lots of plants, will we have animals? And he gave a good reason why there would be animals if there were plants. But as we get onto that.
Right. Tim, some thoughts on the universality of the sort of stuff we're talking about?
Well, I think more questions than thoughts. I mean, one question that I'd like to ask Martin and you is what the situation is as to whether you believe that the likely situation is that there is that life has actually spread around the universe. The idea that the origin of life didn't actually start on Earth, but came in as some sort of cosmic dust which generated the start of life on Earth. That seems to me quite an interesting sort of initial question, because that determines the diversity we can expect. So that if it's the case that we believe that our own life started as a result of some sort of injection from some other planet, then we can, I think, expect similar variations which are much more similar to our own within reach. That doesn't, of course, mean that there are no other origins of life, but it obviously slightly narrows the range of what we're thinking about. And I think that's out of my field. So yes, I think I have to turn that over to you and Martin.
Yes, well, can I comment? I mean, I think this panspermia idea is possible, but you've got to have the origin of life somewhere. And it seems to me that there's no advantage in saying it's a long way away and then came here. But to give the history of the subject, Fred Hoyle was a great believer in this. But he had a stronger motive than we do now, because he believed in a steady state universe where there was an eternal past. And of course, if you think the origin of life is very, very rare, then of course, if you've got an infinite time in the past, that makes it easier than if you're stuck with the limiting time frame of our present universe. So he had a good reason for saying it might make sense. Whereas now, our Earth is 4.5 billion years old, and there are probably no planets which are much more than twice that age. So in terms of the time for a rare process to occur, you only gain a factor of about 2 in our present universe. And so that makes me bet more strongly against panspermia being important than I would have done if we'd been in a steady state universe.
I think another interesting thing about it is that you say that maybe in that case there would be less diversity, but of course, even if Earth had received a delivery of a very simple, either a very simple organism like the last universal common ancestor, a single organism that's the origin of all life on Earth, well, still the diversity that we have on Earth is still pretty diverse, and that all came from that one ancestor. So I think that you'd still expect diversity. I mean, what's interesting, I suppose, is to think about whether the essence of life on Earth, so DNA, whether DNA is really something special. Perhaps it was not an organism that was delivered to Earth from outer space, but DNA, and how that would constrain life on other planets. Which it would, of course, you know, then there are some things about DNA, like the fact that if you reproduce sexually, you have 2 parents, that aren't necessarily true with other biochemistries. So there might be some constraint there if we did receive organic material or organisms from other planets. But I think, like Martin says, I think space is so large, distances are so large, time is a lot shorter than people often think. So I think it's probably less likely than independent origins.
Okay, I suppose there's one other thought there, which is that if life evolved not very long after the origin of the planet, and there are so many other planets, we are going to have. It's first of all more likely that there are other planets where life evolved separately, because it didn't take us that long to generate life on Earth. And secondly, we're going to see planets, or we may see planets, where life has evolved, and where the different transitions from algae to plants to animals have occurred at very different stages. So that the actual time involved varies. I'm struck how recent much of the evolution of what we think of life on Earth actually is, how comparatively recent the mammals are, and so on. And it seems to me that one exciting possibility here is that we're going to, if there is life on lots of other planets, we're going to find planets at different stages of the development of life, and that will tell us something about the grand picture of life, and what the sequences are through time, and how long life lasts, perhaps on particular planets, and conceivably what wipes out life on planets in a way that we don't know about at all at the moment.
Yeah, and there's a couple of interesting things there, because of course, although as Martin says, you know, there are no planets that are 10 times older than Earth, but most, from what we've discovered, most planets that we've discovered seem to be quite a bit older than Earth, maybe, you know, say twice as old as Earth. Well, you know, life has been around on Earth for 3 billion years, and only in the last 500 million years has there been really very complex life like we're familiar. So even twice as long is far longer than complex life has been existing on Earth. So yes, it'd be really interesting to see what kind of life could exist there. But then the other point, as you said, is that we don't know what's triggering these transitions, and we sort of think that many of these transitions were triggered by global events or even astronomical events, meteors that wiped out the dinosaurs, for instance, but other events that caused massive ice ages and things like that. And so it could be that there's a very old planet that simply hasn't gone through those stages because it hasn't had the triggers that it needed.
And I suppose starting up with what you were saying, I mean, you painted the picture of saying that in very general terms, there's gradually through time been an increase in complexity. Made me wonder whether if we look at current biodiversity crisis, whether we're actually going to see patterns of initially being an increase in diversity and complexity and then a collapse of both, perhaps ending up with a very small number of clonal organisms which take over the planet.
Yes. Well, of course, this brings up the question of the future when technology emerges in a civilization. And of course, we don't know, I guess, how probable that is. I mean, some people would say that it's inevitable, whereas others would say it depends on rare contingencies. If you reran the clock, you wouldn't get it. But of course, if we think of the future of the Earth, and of course, in principle, it could be longer than its past because the sun has another 6 billion years to go, then we don't know what would happen. I mean, we could be wiped out and a new creation could get started again. But the other possibility, of course, is that we, or humans, do develop a bit further. And then, of course, any future evolution will be what I call secular intelligent design. It won't be the winning selection. And this, of course, may lead here on Earth and maybe in other planets, which we could then spread to new entities. And of course, the other possibility is that human beings may themselves be replaced by some post-human entities, which in a technological civilization could be partly electronic in some way. And that therefore means that when people look for alien intelligence, then I think that if they find anything, and I'm not holding my breath, then it's more likely that it'll be something electronic, which may be a legacy of some long dead flesh and blood civilization, because something like that could last for 1 billion years. Whereas if we think of our technological civilization, which has existed for a few millennia, it may either be wiped out or transmogrified within the next century or two.
Yeah, and it's one of the, of course, one of the most popular explanations for why we haven't seen aliens is that once they reach the technological level,
it could be much more long-lived.
Sorry, yeah. So there's this that you reach technological level where you're just toxic to yourself. I mean, I'm slightly going to go out on a limb with an idea that's not. I don't think it's totally accepted, but we do know that if we look at the fossil record and we try to estimate biological diversity over geological time, we see that diversity has been increasing pretty steadily in terms of the number of different organism taxa, the sort of different types of organisms that are around, fairly steadily since the last really great mass extinction, 300 million years ago. So, but before that, diversity seemed to be fairly constant. So there seems to be this idea that once an ecosystem reaches a certain level of diversity, once there are enough different kinds of things, flowering plants and crawling animals and insects and so on, then it's really quite robust to extinctions. So the rebound from the mass extinction 66 million years ago when the dinosaurs died was very quick. And so one might speculate that even if we do a terrible job and we really wipe ourselves out and wipe out half of the species on the planet, there may be enough diversity here now to allow a relatively fast rebound from that, and so we may see that the process start again, but that's pretty speculative.
But would it lead to intelligence like ours fairly automatically or not?
Well, what do you think, Tim? This really ties into like why societies form and things.
Well, I'm just very struck that the prediction of our seas as a result of overfishing is basically that they'll be taken over by jellyfish, and jellyfish do hugely well when the fish are removed. And so you move to a much simpler life form. I'm also struck that there are these ant species where single clones now exist across more than one continent. So they're taking over huge areas of ground, and wonder whether we shall actually just see a great simplification of life on Earth as a result of human impact. Maybe that's a dystopian possibility, but what we're seeing at the moment is human eradication of a large segment of life, and if that keeps going, it seems to me where we may move to a situation where not jellyfish per se, but jellyfish rule.
Perhaps I could just suggest we open it up to some of our listeners who've sent in lots of questions, actually. There's a question from Peter O'Sullivan. He talks about what the trigger for life might be, and particularly mentions a meteorite and how it was found to have contained organics and amino acids, the ingredients for life, he says. And is this how we think life might be triggered on other planets or other parts of the universe by the movement of meteorites and matter in that way around space? I don't know if anyone wants to sort of respond to that. He talks about a particular meteorite sort of near where he comes from in Winchcombe.
I think that a lot of the work on origin of life now has moved beyond the question of where amino acids come from. We're actually pretty sure that amino acids are pretty common in the universe, surprisingly so. You find them in outer space, right? And you can make them quite easily. The real difficulty seems to be putting them together. And no one's really come up with a good explanation of how you go beyond that step and form molecules that are stable and can replicate and so on. So I think the delivery of the building blocks probably isn't as big a problem as we once thought it was. Certainly, we did once think that was a big deal. I don't know, Martin. Do you know any more recent stuff on that?
I don't know. I mean, I agree with you. Amino acids are widely dispersed in space, so it's the next step. But to slightly generalize the question, if we understand the origin of life on Earth, and as we know, serious people are working on this, it was a topic in the too difficult box that not very many serious people worked on, whereas I think, as we know, there are some really serious people working on it now. That will tell us whether it's a rare fluke or not. But it will also give us some clues on whether DNA is a good way of making life, or whether people might then explore whether there could be other kinds, maybe even some that don't need water and could be based on methane and could therefore exist on Jupiter's moons. We just don't know.
Thank you. There's another question here, which is about interspecific communication and emotional contagion from Shelley Volsher. Based on evolutionary biology and the ideas in your book, Arik, do you think we would experience some sort of contagious effect with species from other planets? I don't know if anyone would like to.
Those will definitely fit.
Yep.
What do you reckon, Tim? Do you think that there would be enough in common between us and life on other planets to have interspecific relationships?
Well, I think that goes down to quite an extent as to what the form of communication is. So if you have, you speculate on that, and if you have some sort of common language that you can understand, then there's a chance of that. It seems to me that the range of emotions is closely tied up with cooperation and competition. And so you're likely to get a range of emotions associated with that, unless you move to, again, the kind of thing you think about, you talk about, where one's dealing with a very specific group of organisms that all interact, where there are no predators. You make the case that, and I think convincingly, that they're likely to be predators. That it's difficult to envisage a situation where there isn't competition. So I think you're always going to get an intertwining of competition and cooperation, the two sides of the coin. And I think that will generate a lot of the things that we think about as examples of emotions, which are tied up with empathy. And empathy is a good way of basically predicting what someone is going to do to you next.
Yeah, I mean, and I would agree. And I think that we need to remember that the reason that we have domesticated dogs so successfully is not because they are earthlings, right? It's not because we have the same DNA. It's because we have the same social structure, similar social structure, and so there was that ability to understand the communicative signals in another species. Yeah, sorry, Martin.
No, I was just going to say that if we're thinking of intelligent species of that kind, then of course the question is going to be, are they going to be mainly electronic or not? And as I would see it, this is relevant to the so-called Fermi paradox, which is that if life is common and a fraction of it does evolve, as has happened here on Earth, leading to people like us, then why aren't there some which have had a head start and which have manifested themselves by coming here, etc.? I think that's a non-trivial argument, but the way I would get round that as a possibility is to say that if we think of what are called posthumans, whether they are flesh and blood or electronic, then they will not have evolved by Darwinian selection, but by design. They'll have been designed by humans modifying them. And whereas Darwinian selection favors intelligence, but also, I guess, favors aggression, this kind of artificial design of new species doesn't necessarily require aggression. So it could be that there are, as remote descendants of species like us, entities out there in space which are thinking very deep thoughts, but are not aggressive or territorial in any way. And this is a way of reconciling the Fermi paradox, the fact that we haven't been invaded, with the possible existence of a whole lot of entities that could have, in some sense, mental powers far beyond what humans have.
That's
an alternative. Is an alternative then that a situation where you have non-human life that is actually competing intensely, so that you have instead of natural selection operating on biological replicators, you have natural selection operating on electronic replicators who have very little of the empathy and are quite happy to exterminate each other on a regular basis.
Yeah.
Was that, sorry, I think Martin was speaking there.
Yeah.
bit frozen.
Yeah, I think you might have frozen slightly, Martin, for a moment there. I was just wondering actually whether what you just said, Martin, is an answer to one of the questions that we've got here from Jonathan Lowe. If the oldest planets in the universe are up to twice as old as Earth, should we expect to have been detected by now by more advanced life on some other planets? In other words, that other people should have found us rather than us finding them. I think what you just said is a sort of answer to that kind of attack, isn't it? That kind of question about whether life can't be there because it would be, it would have discovered us. And I think you were sort of arguing perhaps that life could be of a very different type, that wasn't competitive, and it wasn't going to invade, and it wasn't going to attack. Those were not part of other forms of life. I may have misunderstood. Oh, I think Martin's frozen again.
I think we may have lost him a little bit, but
yeah.
No, back. No, but I think Tim's point is an important one, which is that we like to think that that sophisticated, designed artificial intelligences are thinking deep thoughts and all being nice to each other. But of course, the alternative is that they're just very, very good at competing with each other, and they're very good at fighting each other. And it's not immediately clear that a universe full of very intelligent aliens would necessarily be coexisting in harmony and wouldn't in fact be competing. Although that's quite a big question to try and answer in one go. I think all we can say is that at least that those two possibilities are open. Competition isn't excluded by the fact that you're very intelligent.
In which case, there's quite an interesting issue. I mean, if we have life like our own, then we surely have to beware of the danger of epidemics, intentional or unintentional. And if we're moving to a situation where the replicators are electronic, we have to beware of intergalactic malware and attempts to disrupt on a major scale.
Well, I know that's something that Martin writes about, so I don't know if the connection's working, we should get his answer to that. I don't know. Well, while he's working on that, my take on this is that I don't think we need to worry. I think that the distances in space are so large that a civilization that were capable of traversing these distances and had an interest in traversing these distances would have no real reason to colonize us, as it were. You know, when Europeans went to the Americas, they wanted gold, they wanted other produce, but you know, if you've got the energy that can propel you at the speed of light from one planet to another, then you've probably got all the energy that you need. But I don't know, maybe we can get Martin in on this one.
Not sure if we can get, maybe just while Martin is getting connected, I could just ask another question which comes from David Clary. Is it becoming possible to detect and identify molecules of increasing complexity in various astronomical environments? Is this providing clues to life outside the Earth? You know, I suppose the sensitivity that we now have to find these materials and these chemicals and molecules, is that something who'd like to? Arik, do you want to?
Let's see. Martin, can you hear us? Can you hear us? No? Okay. Yeah, so it is being done. Now this is the big new field that can we detect chemicals in the atmospheres of planets around other stars, and we will be able to. We can't quite do it now. We're very, very close, and there's still a lot of interesting work going on detecting in looking at planetary atmospheres. So as they pass in, as they're going around the star they're orbiting, they pass in front of the star. There's a brief period of time where the starlight is shining through the atmosphere, and you can use that to find out what's in it. A much bigger problem is deciding what it all means. So if we see oxygen, for instance, does that mean there's life? Well, not necessarily. So it has to go hand in hand with a lot of modeling, a lot of modeling of the chemical processes that might be taking place in an atmosphere. But we're certainly hoping, particularly with the new great big telescope being launched into space, hopefully very soon, to see those kinds of results. Yeah.
Thank you. And there's another sort of related question about what sort of evidence one might have from Charlotte. Would it be possible that our detection of extraterrestrial life may be via sound or another sense, radio or other, is the question. You know, I suppose a question about what kind of evidence of different types we might have for extraterrestrial life. I don't know, would anyone, I don't know if Martin could hear that.
Still struggling with the tech.
Yeah.
I think intentional signals are one thing. So you know, if really the only way we're going to sense messages from other planets is if they've already reached a technological level where they can send messages out into space. If we were to visit some of these planets, then what kind of sensors are they using? What kind of signals are they sending? That's a really interesting question. But again, it's down to the laws of physics. It turns out there aren't that many ways that organisms can send information. So sound is a really good one. If you've got an atmosphere, it just works really well. Light works quite well under some circumstances. They may do things that we don't do, like communicate with electricity or with magnetism. But again, these are things that we see on Earth. These are things that there are plenty of animals on Earth that communicate with electric fields, and so we can study those and understand from them what might be a useful way of communicating on another planet as well.
There's a series of questions sort of related to the same topic in a way. They come from different angles. Conal O'Donnell, David Bridges amongst them, really about life that seems to have sort of gone to sleep and whether it might be possible for it to be awoken. I suppose the question being if there is the possibility of life in other planets which is dormant, and that there would be some way in which it might be awoken or come back to life in the way that we know that sometimes on Earth there are plants and animals which seem to be dormant and then after a long time in hibernation come back. Is that a possibility? Do we think that there could be life which is not, as it were, visible? It's not moving around, it's not behaving in that way, but that it's hibernating, and that if we found, we would be able to sort of reactivate it in the way that sometimes happens on Earth. Who'd like to? Martin, did you want to say whether you thought that might be a possibility? No. I'm not sure if Martin's got any audio actually.
No.
Okay. Arik, do you want to?
I think, I mean, the obvious question there is then, what are they doing while they're hibernating? You know, if an organism hibernates for 10,000 years, it's not evolving while it's hibernating. So if it's active once in 10,000, 1 year in 10,000, then evolution is going to be taking place 10,000 times slower on that planet. Is it really going to is there really going to be time for that to evolve? Well, one could envisage a situation, for instance, where the planet itself experiences drastic changes in conditions, and this may be necessary. There may be 10,000 years of uninhabitability, but that's going to have some pretty serious effects on the way that these organisms can interact and if they can evolve together or not.
I think that's an interesting issue, but I think that the sorts of periods of dormancy that people are thinking about are fantastically short compared to the millions of years that we might be thinking about. I don't know of any cases where life has reappeared, where species which were dormant have reappeared after thousands of years. And I mean, I certainly don't know about this myself, but I wonder whether it's known how long life that goes dormant, organisms that insist, that become cysts or anything like that, can in fact last. I suspect it's not known. I suspect it's probably much longer than the normal dormancy periods that we see, but whether it's actually running into 10,000 years, whether you can get seeds that germinate millions of years later, I rather doubt, but I don't know. What do you think, Arik?
Well, I think since we're coming right to the end, I think it's a good ending point is just to remind people that simulation studies have shown that the asteroid that sent the dinosaurs extinct ejected so much rock into space that it's very likely that some of those rocks will by now, after millions of years, have reached the moons of Jupiter and Saturn, and that it's possible that bacterial life on those rocks could have survived that journey of millions, literally millions of years, in which case we may end up getting to Enceladus and Europa and finding the descendants of Earth-based life on those moons.
I think we've just sort of got to the end of the time that we have allocated. It's been absolutely fascinating. I'm afraid there's still loads and loads of questions that we haven't managed to talk about. I do apologise, we haven't got to all of the different questions that have come up on the Q&A, all fascinating questions. It's obviously a topic which has really impressed people and got people really thinking about all sorts of things, you know, about whether life is a fluke, that it's kind of one-off, how we would spot life, what sort of triggers there might be for life, how we can infer things about other planets, what evidence we would need. And I think, Arik, your introduction and discussion with all three of you has been fantastically illuminating. And you can just see from the number of questions on our Q&A how much it's inspired people to think about this topic. So may I thank you very much indeed for your time and for joining us this evening. And I've learned a huge amount myself and I've really enjoyed it. So thank you very much indeed.
Thank you.